AP Calculus BC, Unit 8, Day 4 lesson. Here's a warm-up for you guys to try first. Just everything in section 1 down to this line right here, okay? We're going to find a Taylor polynomial for the first 4 non-zero terms centered at 0, which is actually a special type of Taylor polynomial called a MacLaurin. And it's the first 4 non-zero terms and centered at 0. Now, you can use this table to kind of help you. I'll go ahead and help you guys out on the first one so that you can know what to do on the next part. So, this is the pattern. Specifically for MacLaurin series, you plug the center in, which is 0 here, and usually you have like an x minus the center, which is going to be 0. So we could use x equals 0 for the center. We're going to save this one for one later. And then x equals 0 here, and x equals 0 here. So we can use these. So the first thing you might want to do is crank through these derivatives. So 2 cosine 2x, you got to remember the chain rule. -2 sine 2, or -4 sine 2x, -8 cosine 2x, positive 16 sine 2x, 32 cosine 2x, -64 sine 2x, -128 cosine 2x, and positive 256 sine 2x. So it's not super hard, but it's a little tedious. Then we're going to evaluate them at 0. So this table is just to kind of help you organize it. So you just plug 0. Sine of 0 is 0. This one's going to be 2, 0, -8, 0, 32, 0, -128, 0. Okay, and then you're gonna write the series. So we skip the 0 terms, but remember that they go with that derivative. So the first term is going to be 2x to the first power over 1 factorial. The next term is going to be -8x, not x squared, x cubed over 3 factorial. The square term had a 0 coefficient, so it's gone. Then 32x to the 5th over 5 factorial, and then -128 x to the 7th over 7 factorial. We could then try and simplify it, write a little nicer. This is the same thing as 6 times 4 is 24, times 5 is 120. 7 is just really big. What I might do is just write it out and then start trying to reduce it that way. So first term is 2x. Next term is going to be -4/3 x cubed. Those ones aren't too bad. I would take 2 out of both of these, and then 2 out of both of these, and 2 out of both of these. So it's going to be 4x to the 5th over 1/5 over just 15. I don't know what. And then the next one, we could take a 2 out of this. That's going to be 64. You can take a 4 out. That's going to be 16. You take a 2 out of this. That's going to be 8. So I think it's going to be -8x to the 7th over what's left. All these things multiplied together. 21, 105, 315. So that's your final simplified answer. So that's what we're doing. That's what you're going to do on these next ones. So go ahead. As you're doing these multiple derivatives, sometimes there's patterns. Try and look for the patterns to take advantage of them. So pause video and then go ahead and finish those 2. Leave this column blank. We're going to use it later. Okay, assuming that you've tried all these, the next derivative here, chain rule, 2e to the 2x, 4, 8, 16, 32, 64, 128, 256. So crank those out. If you plug 0 in, all they eat at the zeros become ones. And so you have 1, 2, 4, 8, 16, 32, 64, 128, 256. More than necessary. But okay, so the series is going to be like this. We're going to start with a 1 times x to the 0 over 0 factorial. Now that's 1, that's 1. Okay, because we actually had a value up there. We didn't have it on the sign. Then we go to the square term, 2x squared over 2 factorial, and then 4x cubed over 3 factorial, and then 8x to the fourth over 4 factorial. And then we could go ahead and simplify them. First term is 1, and then plus x squared, and then this is 6, so it's going to be 2/3 x cubed. I think let's make sure. Oh shoot, I skipped it. That's supposed to be 1 factorial, 2, 3. So let me back up. This should be 1 plus 2x squared. That's going to be plus 2x cubed. This is going to be 6. So that's going to be plus 4/3 x cubed. So I messed up a little bit there. Okay. All right, next one. Now, the next one is a little trickier because you got to do product rule. So you do x times derivative of e to the x, which is e to the x, and then you got to do e to the x times derivative of x, which is just going to be derivative of x is 1. So you get that. Next one, you're going to do that product rule again, which is going to be x e to the x and an e to the x. But there's another e to the x whose derivative is e to the x, so you're going to have 2 e to the x. So you might notice the pattern here, x e to the x plus 3e to the x. X e to the x plus 4e to the x. So if you look for the patterns, sometimes that can speed things up. Now, if we plug 0 in, all these first terms drop out because they all have 0 times something. So you get 0, 1, 2, 3, 4, 5, 6, 7, 8. So those are our coefficients. So the first term is 0. So we don't write. We want the first 4 non-zero terms. So then we're going to 1, but that's at x to the first because that's the first derivative, right? That one had a 0 in front. Plus 2x squared over 2 factorial plus 3x cubed over 3 factorial plus 4x to the fourth over 4 factorial. And we get x plus x squared plus x cubed over 2 factorial, which is 2, right? Remember, 3 factorial is the same thing as 3 times 2 factorial. And 4 factorial is the same time as 4 times 3 factorial, so the 4's cancel. Plus x to the fourth over 6. So that's how we can build a Taylor polynomial, MacLaurin polynomial for any series. Like that's a process we go through. Now, we're often going to be able to take advantage of some shortcuts. So I'll talk about that. In fact, I guess right now I could go and bring it up. This is a sheet that is in your book. It's a list that's in your book, and I'm probably going to give you guys a copy of it. But you'll notice there's a bunch of 1, 2, 3, 4, 5, 6 very common Taylor series. And we can actually construct a lot of other series from these ones. So 1 over 1 minus x, that's the most basic power series. That's when we started with a equals 1 and r equals x. That's the simplest, most straightforward power series. We'll encounter other versions of that sometimes. E to the x, very famous, has a very clear pattern. Cosine x and sine x come from e to the x. Cosine x is half the terms. It's all the even terms, and cosine's an even function. So I feel like that makes it easier to remember, right? Even function, even terms. Sine is half of the terms of e to the x. It's the odd ones, and it's an odd function, and you take the odd terms. Now, they both have, e to the x is all positive the whole way through, where cosine and sine have this alternating sign, so you need to put this extra negative 1 to the nth power to make sure it flips back and forth. The first term is always positive for both of these. So I memorize all three of these together because these are half of that. Natural log came from, if you forget, I mean, we're going to write these, we're going to do some of these in the notes right now too. So I'll just come back to it. But sometimes you want to actually just use these functions. So like we were just doing sine 2x, and these are MacLaurin specifically, okay? These are centered at 0. So you could say, oh, well, sine 2x, let's take the sine function and plug 2x in for all the x's. Whatever's being done to the x has to be done to 2x. And look what you would get the right answer. You would get 2x minus 2x cubed, which is 8x cubed. That's how we got the 8, plus 2x to the fifth, which would be 32x to the fifth. Like we could have totally used this and just plugged 2x in to get this series. E to the 2x, same thing. Everywhere you see an x, put a 2x. But the x is squared, so 2x is squared. It's 4x squared. Right? 4x squared. Yeah, I don't know. Just make sure that what I'm saying makes sense. 2x. Let me check my answer. Yeah, I mean, oh, you know what? I messed up when I was doing my work here. This is the first. This is the second. This is the third. So 4x squared. I messed up on that when I was doing it in the warm up. I got that one right somehow. That's weird. Okay. Yeah, but we could have gotten that one from that. X e to the x. We could have just taken the e to the x and distributed x to all of them, and it would be the right answer. Right? If you just distribute x to this, you get x squared, x cubed over 2 factorial, x to the fourth over 3 factorial. And if you just distribute an x. So, kind of a cool trick that we could use. All right. So we're going to try and do that as much as we can in the future, but sometimes you still have to do it the old way. Now let's go and sort of take our warm up further. The Taylor series centered at A, we wrote it for a MacLaurin series up here centered at 0, but the center could be at different places. And so those shortcuts I was just talking about, those are all MacLaurin series. So you might get stuck not being able to use that if it's center something else. So it's the derivative at A, x minus the center A to the 0th power over 0 factorial. Now that's just going to be 1. That's going to be 1. And this is like the 0th derivative, which is the original function. People always forget to put that term because they are, oh yeah, it's always the derivative at the center. And so they start at the first derivative and they neglect the first 0th derivative essentially. X minus a to the first power over 1 factorial. It's this very simple pattern. Second derivative, second power, second factorial, right? Third derivative, third power, third factorial. So the closed form of it, if you start at 0 to infinity, is going to be the nth derivative at the center, x minus a to the nth power over n factorial. So that's for any kind of Taylor series. And you could apply this to MacLaurin series centered at 0. You could start with this and it works. So let's go ahead and do one of the problems we did in the top. We've already done a lot of the work for it. Find the Taylor polynomial of the first 4 non-zero terms centered at pi. So we're going to do this one right here, but centered at pi. Now, we would take all the derivatives. Now, that shortcut I was talking about using before, I don't think we're going to be using it if it's not centered at 0. So we plug pi in. Sine of 2 pi is 0. Cosine 2 pi is 1. Sine of 2 pi is 0. Cosine 2 pi is 1. So it's interesting. We actually get all the same values. Okay? Get all the same values that are going to help make the coefficients. But now, the first one, so we're doing 2 x minus the center pi to the first power over 1 factorial. That's the first term that we have a value for. And then we go to this one, which is for the third derivative. Negative 8 x minus pi to the third power over 3 factorial. And then the next one is 32 x minus pi to the fifth power over 5 factorial. And then the next one is negative 128 x minus pi to the seventh power over 7 factorial. If we were to simplify these, I think we'd end up getting the same kind of values that we got on the first time. So if we could cheat and kind of just use them. So that's how you do a Taylor series centered anywhere. Okay. So you got to understand that, be good at that. There will be opportunities for shortcuts. Next page, I'm going to go through a bunch of those really common series, which, like I said, there's a list of in the book, and I might give you a copy, a handout of it. But let's just kind of walk through them again and just understand if we had to, we could recreate them. Okay. Because it's not going to, those aren't going to be given to you on the AP test. I'm not going to give them to you on your test. You're not going to be able to, you're going to sometimes have to recreate them. Most of them are pretty doable to recreate. Okay. So this was the most sort of general power series. The very first one I ever showed you. And what it was a geometric series with A equals 1 and R equals X. And power series come from when R has X's in it. And the simplest one would be R just simply equals X. The first term is 1. And then this is R equals X plus X squared plus X cubed plus X to the fourth plus ... You need to be able to write these in closed form also. Okay. And it's kind of half memorization. It's half thinking about what you're doing. If you try and memorize all these 100%, you're going to struggle. It's going to be hard. You're going to mess it up. If we start at 0, you can always just put like in values over these terms and try and figure out the pattern is. This is just going to be x to the n. Okay, now this converges from -1 to 1, which we could also figure that out ourselves. We could do the absolute value of r, should be the absolute value of x, has to be less than 1. And if you solve that absolute value inequality, that's what you get. So that makes sense. Now, some of these, if we did that for, things, we get some sort of surprising results. Now, the e to the x one, you're just going to memorize. It's essentially, it's x to the 0 over 0 factorial plus x to the first over 1 factorial plus x squared over 2 factorial. So it's x to increasing powers of the same factorials. Now that's going to be 1, that's going to be 1. So that first term is just going to be 1. And then that one's just going to be x. But that's the pattern, x cubed over 3 factorial plus x to the fourth over 4 factorial. It's a pretty simple pattern. Memorize it, okay? We're not going to want to try and recreate that one, okay? It's going to be x to the n over n factorial. It actually converges for all real numbers, okay, which is kind of a surprising result. But we're not going to get into that now. We'll talk about convergence and intervals of convergence more next chapter. Now, sine, the thing I memorize about sine is you could recreate both of these from scratch using the method we did in the warm-up. Or you could remember that this is an odd function and it's half the terms of e, so it's all the ones with odd powers. It's x to the first over 1 factorial, it's x cubed over 3 factorial, it's x to the fifth over 5 factorial, it's x to the seventh over 7 factorial. Now there's another pattern. The first one's always positive, negative, positive, negative, positive, ... Okay? So it's flipping back and forth. E to the x doesn't do that. E to the x is all positive. So then the closed form, n equals 0 to infinity, it's going to be, now we can't just say x n over n factorial. This is n equals 0. This is n equals 1. The terms that are gone, we don't count those. So we got to figure out a pattern here. Whatever the exponent and the factorial are, it's the same number. So it looks like it's 2 times the n value plus 1, right? 2 times the n value plus 1. 2 times n value plus 1 over 2 times n plus 1 factorial. It needs to be in parentheses. We also need something to give us the negatives. So I should have squeezed it in there ahead of time. But negative 1 to the nth power, we want to raise it to the 0th power first, which makes it positive. That should work. This also converges for all real numbers. Which is kind of crazy, but we'll just accept it for now. Cosine, same deal. It's the even terms of e to the x, including the very first one. X to the 0 over 0 factorial is considered an even term. Okay? And then x squared over 2 factorial, and then x to the 4th over 4 factorial, and x to the 6th over 6 factorial. It's all the even power terms, and cosine is even. Or you could take the derivative sign to get it. I think it's easier just to memorize it on its own. Positive, negative, positive, negative. This is going to be 1. This first term is 1. If you wrote some n values here just to make sure you got the pattern right, it looks like it's going to be, you need a negative 1 to the n, and then it looks like x to the 2n, x to the 2n, x to the 2n over 2n factorial. You need parentheses around that 2n. Otherwise, the factorial is applied to what it's right next to. Just the n and the 2 comes afterwards, gives you a different answer. This converges for all real numbers. So I memorized those 3 together. Now, natural log, to me, it's hard to memorize this one. But the way we got it was by integrating 1 over 1 plus x, which I think that should make sense, right? If you're like, well, where did this come from? We integrated 1 over 1 plus x, right? And this series right here, first term is 1, and then the r value is negative x. So the series looks like this: negative x squared plus x, negative x plus x squared minus x cubed plus x to the 4th. So if you could recreate this pretty quickly. I mean, if you have to, you try and memorize it, but I think it's hard to memorize. So if you integrate this, the first term is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot, dot, dot. I mean, to me, that's probably what I'm usually going to do, unless I just have it on my memory. I don't think I'm going to be able to effectively remember that long term. If we started at 0, this is an alternating pattern, right? So it's going to have a negative 1 to the n, and then it's going to have an x to the n plus 1 over n plus 1, because remember this isn't equal 0. Now, this one might be a nice one to start at n equals 1. If you did that, it'd be negative 1 to the n minus 1, and then just be x n over n. Same thing. You should be able to write any of these terms starting at n equals 0 or 1 if you had to. This converges from negative 1 to 1, but it actually includes 1. Okay? It doesn't include negative 1, since if you plug negative 1 into natural log of this, you get natural log of 0, which is undefined. So it makes sense that we don't include negative 1 just because the function doesn't exist there. But on these other ones, usually it's negative 1 to 1 and it doesn't include the boundaries, but this one, it does include that boundary. Okay, inverse tangent. Again, you can try and memorize it, but we got it by integrating something. And you guys should know what inverse tangent is the antiderivative of. It's the antiderivative of this, which is a simple power series starting at value of 1. R equals negative x squared. Next term is minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, so on, right? So if we integrate that, you get inverse tangent. So that's x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, dot, dot. So if we were to write the values here, n equals 0, n equals 1, n equals 2, it looks like that Looks like it's just the odd terms. It kind of reminds me of sine to the x. It's not the same. It doesn't have factorials. So it has a -1 to the n if we start at n equals 0. And then it has an x to the 2n plus 1. And then it has a divided by 2n plus 1, no factorial. This converges from -1 to 1 and includes both endpoints. So you need to know these 6 series inside and out. You should mostly have memorized. You should know how to create them quickly. Okay, taking multiple derivatives to get these is the long way. Yes, you can use that for any series, but these ones are special and they came from kind of special cases. So it's good to kind of know where we got them originally and use that to help you remember how to, write them out if you can't remember it. Okay, now here's a fun problem. Some of the most famous numbers in math, 0 and 1, pi, e, the natural number, I, imaginary number. So there's this equation right here, or this expression, e to the pi I plus 1 equals 0, which is a little kind of like, really? I don't know. Are you sure? We can actually prove it with series. And this will actually give you some I'm going to show you how we take advantage of these 6 series and memorize them to just create other series that are kind of off of them. So now remember, just to jog your memory, I is an imaginary number. The square root of -1 is I, right? So I to the 0 is 1. I to the 1 is I. I squared is -1. I cubed, multiply that by an I, negative I to the 4th is +1. I to the 5th, we're back, where it repeats itself. Okay? So we'll keep that in mind. Now, I want to use series. So e to the ix. Let's write that series out. Now, that's the same thing as e to the x that we have up here, but replace all the x's with the ix. So the first term of e to the x is 1. That doesn't change. Plus x, but we're going to put ix. Plus ix squared. Okay. But remember, I squared is -1 over 2 factorial minus I cubed, which gives you -I, x cubed over 3 factorial, plus I to the 4th, which is +1, x to the 4th over 4 factorial. So we'll start with that. And then let's do I sine x. Now, I sine x is just taking the sine x series and multiplying everything by an I. It doesn't get almost any simpler than that. So you just multiply what sine x is by an I. Everything gets an I. So you have ix minus I x cubed over 3 factorial plus I x to the 5th over 5 factorial. And we'll keep going. Okay. And then I'm going to take the cosine x series exactly the way it is. So do you guys have it memorized? It's all the even terms of e to the x1 minus, but alternating, right? X squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 5th over 5 factorial. Okay. And then it keeps going. Okay. Now what I want to do is I want to add these guys together. Okay. So if I add these guys together, which that brings up another idea that we're going to actually see a lot. You can add one series to another series to create another series. So if they said, well, write a series for cosine x plus I sine x, well, you could find these 2 separate series and then just add them together. Now, if I'm going to try and add things together in a nice order. So if you do that, I'm going to put the 1 plus the ix minus the x squared over 2 factorial minus I x cubed over 3 factorial plus x to the 4th over 4 factorial. And then I'm going to just stop there. Okay. Now, what we're trying to prove, now, let's see. Now, what I want you to realize is if you look at this result and you look at this result, they're the same thing. Cosine x plus I sine x is the same thing as e to the ix. So that just equals e to the ix. Okay? So, okay, we're going to go with that. Now, so e to the ix equals cosine x plus I sine x, right? That's what we just proved. Okay? Now, what we're going to do, these are called power series, right? Because they have x's in them. And what you do is if you plug a value of x in, then it becomes what we call a number series because all the x's go away. So we're going to plug x equals pi in so that e to the pi I, if I plug x in or pi in for x, equals cosine of pi plus I sine pi. And cosine of pi is -1 and sine of pi is 0. And so then one step later, I'm going to add the 1 over to the left-hand side to the e to the pi I. And then there's 0 left on the right side. And we have proven that e to the pi I plus 1 equals 0. Okay, today's assignment out of your book. Okay, these assignments are super critical. You need to do this today. Do it today. Check your answers. Get as far as you can. If you get stuck, fine, but at least you got stuck and you're ready to ask questions. Okay. This first week of this unit is probably the most important week of the whole semester, the whole year of Calc BC, as far as like making sure you stay on top of things. Okay. This is going to overflow to the next several weeks of series stuff, but this is the time to get it. I'm taking my time. I'm going through all this stuff. I'm showing you where it comes from over and over again. I'm showing you different ways to do it. I'm making you do it. This is how you're going to learn this stuff. Okay. This is totally different than what we've done before. So do these assignments, do these problems, and be ready for tomorrow.